Okay, here is our next video. We are on this de Broglie wavelengths. So this video is made to follow the video that's on de Broglie wavelengths and the momentum of photons. So if you have not watched that video, go do so now before you continue with this video, because this one uses de Broglie wavelengths to look at what happens when we take matter and waves that happen with matter. Right, that's called the de Broglie wavelength. And there's interference. We'll look at diffraction patterns or double slit diffraction, interference, things like that. Okay, so recap, right? De Broglie wavelength, that is from your equation sheet. You get lambda, and I usually like to say dB, is equal to h, which is Planck's constant, over p, or the momentum of the object. All right, so we get Planck's constant over mass times velocity, and that gives us the wavelength of our matter. As a reminder, things for wavelengths for things like a baseball is on the order of 10 to the minus 34 meters. So that's something we will never be able to observe. It's just, well, okay, not never, maybe, who knows. Something we cannot observe. So we just see that as something that exists and is stationary, as opposed to something like an electron is a nanometers scale, which is something that we definitely know how to observe, right? That's about the same wavelength as light. Okay, so we've got de Broglie wavelengths, right? We took the de Broglie wavelengths of electrons. We're going to take a look at that a little bit closer now. Let's say I take a beam of electrons, right? A beam of electrons, and I have that incident on a double slit. All right, so this is just like before, but now instead of with light, it's with matter. So if we have electrons incident on two slits, what would we expect, right? If you throw a ball at a hole, you throw a baseball at a hole, you would expect that the baseball just goes straight through the hole and hits the screen. So if this behaved like baseballs getting thrown through holes, right, we would expect to just see, right, a lot of electrons hitting to the right side or going through the right slit, and then a lot of electrons going through the left slit. So we would expect a pattern kind of like that, right? That's what we'd expect if this is, we'll call that the center line. We'd expect some of the electrons to go through the right slit, some to go through the left slit, and then just keep going straight from there. This is not what we see. Right? What happens is, just like single slit diffraction or double slit diffraction in the optics and waves unit, we see, I erased the wrong thing here. We see a diffraction pattern because electrons, right, have waves. They are de Broglie diffraction. So the waves that these electrons make interfere with each other. So we get a bunch down the middle. Down the middle. What? Right? Because the middle, it would have to go through right there for the electron to get to the middle. Well, not in quantum physics, right? The electrons, they go straight through the middle of those two slits, apparently, to hit the screen right there. But then off to the side, right, we get some electrons there. We get some electrons at another maxima. We get some electrons even further out from that. Not many, right? And this is what we've seen. We see this diffraction pattern, right, where we get this. We get the intensity graph. I should have that in the middle. We get this intensity graph, and I'll call this location, or y. All right, this intensity graph looks just like it did for single and double slit diffractions, which is just bonkers, right? It's just so weird that we see matter behaving like a wave. But this is actually one of the things that confirmed de Broglie's theory, that matter behaves as a wave sometimes, right? That we get this de Broglie wavelength of lambda is equal to h over the momentum, where h is just Planck's constant. This is one of the things that confirmed that de Broglie actually was onto something, is that we shot matter through a double slit, and it gave us a double slit diffraction just like light would. Okay. Now remember, this follows the same. It's diffraction. It's diffraction. It's just diffraction with electrons, but we get the same equation out of it, right? Where this is that distance there, that's y. Our slit distance, that's d. That's our slit distance, or the distance between the slits. If it's a single slit, right, we get that it's just the width of one slit. So the distance between slits, sine theta, is equal to m lambda, where m, this is m equals 1, this one's m equals 2, m equals 3, all that kind of stuff. Where we have the wavelength, except the wavelength now, this is the de Broglie wavelength. Okay, so we can kind of see this right here where we get d, and then remember sine theta, when we set this up, we can reduce that, sorry, not m, to y over L using small angle approximation. I'll zoom in and say that. Small angle, and I'll say assumption, but small angle assumption, small angle approximation, they mean the same things. So we got this small angle assumption, this small angle approximation, to get to dy over L is equal to m, but then this lambda is the de Broglie wavelength, so h over momentum. Okay, remember this m, that's just numbers. That's 1, 2, 3, whatever it is. Is equal to, times h over momentum. And that is the same exact pattern, the same thing that we see. So here's what we can take from this. All right, AP, I've not seen AP require you to do any sort of calculations on electron diffraction or things like that. But I have seen them do conceptual or qualitative of just if this increases, what happens to this, or for these maxima to get spaced further apart, what would we have to do to the electrons? Right? Well, you use this same equation. You start from d sine theta is equal to m lambda, and then dy over L is equal to m over, and then h over p, right? Planck's constant over the momentum. So let's say I want spacing further. How do we get further, if I can spell, further spacing? How do we get that? Well, right, spacing, we have to first identify what that is. We want y to increase. Okay, so a couple things we can do in this equation, right? We could take d, and for y to increase, we could take d and decrease it. So we could decrease the slit spacing. So to increase the maxima spacing, we could decrease the slit spacing. We could, right, for y to increase, if that's on top, we would need the bottom to also increase. So we could take L increasing. M, that's just an integer. So M, we can't change. We can't do anything with that. H, that's a constant. We can't do anything. Okay, but then now we get to this, right? This is the de Broglie wavelength. Because normally we would say for spacing to increase, you increase lambda. But how do we increase lambda? Well, if we want lambda to increase, that means the bottom, because since we can't touch the top, that means the bottom has to decrease. So we decrease the momentum. We can't change the mass, but we can change the velocity. So I'll say the electron velocity, we can make electrons slower, and making those electrons slower would allow them to bend further. Right? That's just like sound. Right? The longer the wavelength, the more it can bend. In this case, it's just the slower the object, the more it can bend. Everything like that. So the slower it moves, the further it can bend, and the farther toward the side it'll go. Okay, we'll look at a practice problem with that later. But moving on, there's another consequence of this, right? If we were to take, this is called crystal diffraction, essentially. Right? Let's say we have some sort of substance where we get a good crystal structure. All right, let's take. All right, crystal structure is essentially you just have a bunch of atoms all spaced out really nicely, and you get this really good crystal. Um, but here's the thing: is they're not all touching. I know I drew a couple of them touching, and that's just incorrect of me, and I apologize. But this here, they're not touching. Atoms never touch each other. All right, that's called our crystal spacing. We can simplify this. I'll simplify this for us. So I'll delete this all and make it a little bit more straightforward. If we take our crystal spacing, and I'm just going to take these, pretend these are atoms, all right, atoms that are all bonded together. So if we have these atoms all bonded together, let's say I then shoot a beam of electrons. If I take this beam of electrons and shoot it to be incident on this crystal, well, what happens, right, we essentially have right there, that is the width of a slit. Right here, this is the width of a slit. So I'm going to call those, right, D, the width of a slit. Right there is another width of a slit. So this is basically, it's just a diffraction grating. Right, diffraction gratings is just a bunch of lines all right next to each other where we have this. And you can take the spacing of the diffraction grating, but the spacing is that lowercase d still. So that's diffraction gratings, but we're creating a diffraction grating for this beam of electrons. So this follows that same exact equation where d sine theta is equal to m lambda. It's just in this case, right, we'll simplify d y over L and m, this lambda, this is the de Broglie wavelength, right? Because it's because of the waves that happen from these electrons. But this d, this slit spacing, is exactly the spacing between atoms. And AP will give you questions like this, where we get our slit spacing is exactly what the spacing between atoms is. So you can take a look at what's our velocity and the mass of an electron. Typically, it's electrons is what they'll use, right? M doesn't really matter because M is just from adjacent slit or from adjacent maxima to the next maxima. L is the length of the screen. That's typically not going to change. We'll usually look at the relationship here in crystals between D, the slit spacing, and lambda, the de Broglie wavelength, remembering that is a constant over mass times velocity. That's typically what we'll look at and just say, okay, what will happen if what'll happen to the spacing? What'll happen to the spacing if we have a crystal that is further apart, right? And the further apart crystal, that's D. Or what will happen to the spacing if we increase the velocity of these electrons? In that case, the spacing would, with an increased velocity, right? That means lambda goes down, lambda gets smaller, and if lambda gets smaller, then y gets smaller. So increased velocity means a tighter diffraction pattern. Okay. I do have on our next page here, I have a practice problem for us. This is straight from AP. It's a publicly available question, so I'm totally happy going through this. A beam of electrons is incident on a crystal, creating a diffraction pattern. How should the speed of the electrons be changed to increase the separation of the spacing of maxima in the pattern, and why would the pattern change? Okay, how should the speed of electrons be changed? Which means V. Do we want V to increase or do we want V to decrease? To increase the separation, so increase the separation, that means we want Y to increase. Why would the pattern change? So that you can see it's all relating to the de Broglie wavelength. So that's going to explain why. Is something to do with the de Broglie wavelength. All right, well, we set up the same exact scenario. D sine theta equals m lambda, but right, we can plug that in and say dy over L is m, and then lambda, this is the de Broglie wavelength, so h over p, momentum, right? This is just the order, so we don't have to worry about this M. Okay, length, that doesn't change between the slit and the screen. That doesn't change. H, that's the same. Crystal means D stays the same because of that crystal. So as we want Y to increase, right? We want to increase the separation. So how do we do that? Well, to get Y to increase, we have to take the denominator and decrease. So to decrease the momentum, we have to decrease the speed. Okay, speed should be decreased, speed should be decreased. All of a sudden, we've crossed off A and B. Okay, speed should be decreased. And then are we increasing or decreasing de Broglie wavelength? Well, H over P, if we decrease the speed, right, we make the denominator smaller. That makes the numerator bigger. Or sorry, that makes the other side bigger. So the wavelength increases de Broglie wavelength. There is our answer. Okay. I've got one last thing for you, which is mostly it's just weird. I'm actually going to back up to this previous one, and I'll take a screenshot of this, or I'll just copy this over. Copy, and we'll come over here. Okay, and paste. If we are taking a look at electrons, so this is not related to the crystals. This is just looking at electrons coming through a slit, and that's it. And so we'll do one slit here. So electrons moving through a single slit, right? And it's one slit. So we'll just take this and right, that's just our barrier there. Okay. So as we have electrons incident on a slit, here's the thing that we are going to look at now. If electrons are incident on one slit, this stuff is just weird. Okay, this is almost, I would even dare say, weirder than relativity. I know what I'm saying with that. So this is now, if we have this electron beam incident on a slit, right, we've gone over the fact that we'll create this diffraction pattern, right? There's the center, where we get some in the middle, some on the sides, and we create these maxima that kind of go out, all that kind of stuff. But what if, and right, single slit diffraction, double slit, basically the same. So that's with us watching the screen. So we're just taking a look at the screen the whole time. Here's the next question. What if instead of sending through a beam of electrons, what if we send through one electron at a time? So if I send one electron through at a time and watch where it lands, right? This would be like throwing a baseball through a slit in the wall. You'd expect that it just lands right in the middle. And then you throw a second baseball at a slit in the wall, and you expect that it just lands right in the middle, higher, lower, sure, whatever. What we see is if, right, as we're watching this screen, as we're watching the electrons come through, we send one through at a time, and they have run this experiment countless times. It does the same thing every time, right? Because double slit diffraction or single slit diffractions are based on interactions of waves, so interference patterns of waves. So if there's only one wave, there shouldn't be interference, right? Wrong, apparently. So one electron maybe comes through, and then you send another electron through on its own, and it ends up over there. You send the third electron through on its own, maybe it's there. You keep sending electrons through, and they keep just popping up all over the place. And yes, you get more electrons in the center than you do any of these other locations, but maybe, right, there's just one at a time, and they keep showing up just like this. Right? One at a time, and these electrons just pop up on the screen all over the place, and it's totally random. We don't have a way to guess it, but you get this double slit or the single slit diffraction pattern when you send electrons through one at a time. It's incredible. Okay. Have I blown your brain sufficiently? blown your mind to some point where you're done thinking, because I've got one more thing for you. Okay, so we've ran this experiment several times, and that's true. It works that way, and we can't really explain too much of why, because there's only one wave going through at a time, but it still creates an interference pattern. The difference becomes, what if we look at the slit? What if I have, right, let's say I have a little camera. I'll draw this as an eyeball. What if I have some observer watching the slit, watching the electron go through the slit? What happens then is the electrons behave nicely, and we get one row. We just get one line, like the electrons all went straight through the slit, and that's it. There's no diffraction pattern. If we watch the electrons go through the slit, there's no diffraction. But if we don't watch the electrons go through the slit, let's see if I can get this here. If we don't watch the electrons go through the slit, if we just watch the screen, then the electrons create the diffraction pattern where we get the maxima and the minima. So matter changes depending on if we observe it or not. Particles behave differently depending on if we observe them on the screen or passing through the slit. And this is something that I haven't really seen AP test much, but it's on the videos, and I've seen like one question on the question bank, but I couldn't pass up the opportunity to just boggle your little sensical understanding of the world just a little bit more, because this is crazy stuff, and we don't really know why it happens this way, but it does, right? So if we observe the slit, right, if we observe the slit, if I take my understanding and I watch the slit, electrons behave nicely, and they only go through the middle right there, and that's all they do. If we just observe the slit, they look like that. But if we observe anything else besides the slit, if we just observe the screen, then we get the diffraction pattern with all the electrons, and life is weird. Okay, so that'll do it for de Broglie diffraction. Really, essentially, all you need to know is if you can answer a question like this, you're in great shape. De Broglie diffraction, electrons create diffraction patterns when we observe the screen. But then down here, electrons, when you send a beam of electrons through a crystal that has a structure like this, then we can take the spacing, and that spacing is essentially the spacing of a slit for a diffraction pattern. And then this equation applies, and you look at it like any other diffraction pattern. It's just your lambda, your wavelength, you're now looking at this in terms of the de Broglie wavelength with h over p, with mass and velocity. Okay, so there is our video on de Broglie diffraction. If you have any questions, please do let me know. I know this is kind of mind-boggling stuff, but if you can just apply the diffraction pattern equations that we've done with optics, you'll be just fine. Right? Calculate de Broglie wavelength, apply that to a diffraction pattern, and just see would slit spacing increase, decrease, things like that. So that'll do it for us here. Let me know if you have questions, and I'll see you next time.